If you look at the notes, this is an example of a reaction involving two same reactants, which is propene and hydrogen gas, and it gives us the same product, which is propane. But the first reaction occurs in gas phase. The second reaction occurs on platinum metal. So we compare with these two. The first reaction occurs in gas phase, so the transition state is in gas phase. Okay. Whereas the second reaction, the transition state is absorbed onto the platinum metal. So this non-catalyzed reaction, it does not involve absorption, but it involves, the transition state is in gaseous phase, whereas this catalyzed reaction, the transition state is in absorbed on the platinum metal. So when it is absorbed on the platinum metal, the bond between carbon-carbon weakens, the bond between the what you call hydrogen and hydrogen weakens, and there's a partial bond formation between the carbon and the hydrogen of the hydrogen gas, and this is a transition state of the catalyzed reaction, but it will give you the same product as with the non-catalyzed reaction. So if you compare with the catalyzed reaction and the non-catalyzed reaction, the non-catalyzed reaction occurs at lower temperature and it has lower activation energy. It means that the non-catalyzed reaction, it occurs faster compared to the catalyzed reaction which occurs on the surface of the platinum metal. This platinum metal is a catalyst. So the catalyzed reaction with lower activation energy, it occurs faster, very much faster compared to the non-catalyzed reaction. Okay, so the reaction pathway or the reaction direction between a non-catalyzed reaction and a catalyzed reaction, they are different. Where the non-catalyzed reaction has a different reaction direction, a different reaction pathway with lower activation energy compared to the direction of the catalyzed reaction. So that is an example of the non-catalyzed reaction and the catalyzed reaction. So, but one thing about catalysis, okay, a catalysis introduces different reaction pathway compared to a non-catalyzed reaction. Okay, the activation energy of this catalyzed reaction is lower compared to a non-catalyzed reaction, but the product is the same. The reactants are the same. The product are the same, except the direction of the reaction, the research direction. The reaction direction is totally different. Okay, catalysis makes the reaction go faster, but it does not change the amount of the product formation. The amount of product formation depends on the thermodynamic of the reaction. Okay, see, but with different reaction pathway, the energetic or the thermodynamics may change due to different temperature of the catalyzed reaction. So, for example, when you have different reaction pathway, of course, the energetic will change. So, it still depends on thermodynamics, because there is a new reaction direction with the use of catalysis. Okay, but the physical properties of a catalyzed reaction or catalysis may change. Like, for example, a solid may become powdered catalyst after the reaction. So, but the chemical nature does not change. A catalysis just accelerates chemical reaction. It does not change its chemical nature. Like, for example, when you use a platinum catalyst, the platinum before the reaction, after the catalyzed reaction is still the same. Okay, meaning the chemical property or the chemical state of the catalysis and the catalyzed reaction does not change. The property may change. Like, for example, you get powder after the reaction. Before the reaction, you put a solid sample. After it become a powder, the physical property may change, but the chemical properties does not change. So that is a catalyzed reaction compared to a non-catalyzed reaction. Okay. So now we go into rate determining step. Okay, so we have seen, like, for example, a chemical reaction does not occur. Okay, a chemical reaction does not occur a single step. Only very rare. Only some chemical reaction occur single step. But most of them occur in multiple steps. Like, for example, the most simplest, I mean, the simplest chemical reaction you can think of it. Acid plus alkali, H plus plus OH minus. It occurs in single step, huh? H plus plus OH minus, you get water. Okay, it occurs in single step. But most of the chemical reaction, because there are bond breaking, bond formation, it occurs in multiple steps. Okay, so the slowest step, like for example, this is a series of chemical reaction. Stage 1, stage 2, stage 3, stage 4, stage 5. Okay, we have 5 stages. Okay, so in this series of chemical reaction, uh, not all of them occur at the same speed. Some can occur at very fast, some occur very slow. Okay, and some intermediate. So many, not all of them, not all of these steps occur at the same speed. Like for example, step 1 can be very fast, step 2 can be faster, step 3 can be fastest, and then step 4 can be the slowest, and then step 3, and then the final step is just intermediate. So this chemical series of reaction, it does not occur at the same speed. Okay, some step can be very fast, some step can be very slow. For example, one analogy. Okay, think about someone traveling from a starting point to a destination. Okay, stage 1, stage 2, stage 3, stage 4, stage 5. Okay, stage 1 is 3-lane highway, stage 2 is 2-lane highway, stage 1 is single lane, stage 4 is 4-lane, and stage 5 2-lane. Okay, so we expect that stage 3 is the slowest because it is single lane road. So single lane road, you have lots of traffic jam. So the journey in stage 3 will be the slowest, we expect, because it is single lane road. Okay, and the journey is stage 4 is the fastest because it's 4-lane highway. So it is the fastest. So therefore this series of chemical steps can be made analogy, we can make an analogy for this series of chemical reaction by someone traveling from a starting point to a destination point. Okay, so when we have A plus B is the reactant. When it reacts, it gives the intermediate. I is the intermediate. Intermediates are basically molecule, atom, or ion being formed after the reactants has react and before the product formation takes place. Those are intermediate. Okay, intermediate will not last long in the reaction mixture. It is the concentration will go up and then it becomes constant and then it goes down. When all of the intermediate has reacted, it finally gives us the product formation. Okay, so like for example here again, say for example, if the third step is the slowest step, so this step is known as the rate determining step. Okay, when the third step is the slowest step, it is known as the rate determining step. Okay, so therefore this step controls the overall reaction rate. Overall reaction rate is controlled by step number 3 because it is a slow step. Okay, like for example, if you want to think about it. Okay, think like someone traveling from starting point to destination point. Okay, stage 1, let's say, it takes us around half a minute. Stage 2 takes you around 40 seconds. Stage 4 takes you around 5 seconds. Okay, and then finally stage 5 takes you around 10 seconds. Okay, so you have 30 second plus what you call 10 second, 40 second, and then you have 5 second plus 45 second, and then you have what you call stage 5, 15 seconds. So many stage 1 plus stage 2 plus stage 4 plus stage 5, you add up all together, it is 1 minute duration. Okay, but let's say stage 3 is 1 hour. Okay, so the whole vertical journey takes you, the time takes you 1 hour 1 minute. Okay, stage 1, stage 3 costs us 1 hour. Okay, but stage 3 costs us 1 hour. Stage 1 plus stage 2 plus stage 4 plus stage 5, the total of 1, 2, 4, and 5 is what you call 1 minute. Okay, because the road is very large and lanes are very free. Yeah? Okay, so stage 1, 2 plus 2 plus 4 plus 5 takes you 1 minute, but stage 3 gives us 1 hour. So which is the rate determining step. The slowest step is definitely stage number 3 because it takes us 1 hour. So you compare 1 hour with 1 minute is a huge difference. Okay. So therefore, the slowest step in the series of reaction is the rate determining step, RDS. Okay, same like for example in a chemical reaction. So you go to compare the chemical reaction. Okay, compare the chemical reaction. You have 1, 2, 3, 4, 5 stages. Okay, so which one of these is the slowest step? Then that is the rate determining step. That rate determining step controls the overall rate of the whole reaction in the reaction mixture. So the RDS, or the rate determining step, is the slowest step in the whole series of the the whole series okay, of chemical reaction. You have reaction number 1, number 2, number 3, number 4, number 5. Finally, after number 5, you get the product formation. So this is an analogy between someone traveling from a starting destination to a final destination. It has the same analogy as a series of chemical reaction, because now we actually measuring the time taken for reactant A plus B to give us the full product formation. So now remember that the rate determining step is the slowest step, and that step controls the overall rate of the whole reaction. Okay. So now, for example, let's say stage number 3 is the slowest step. You go back to the journey. Number 3 is slowest step. So how to increase stage number 3? How to increase the speed of stage traveling in stage number 3? For example, you can build an overhead bridge or a tunnel or what do you call an overhead bridge. Okay, so you can make extra lanes. But in a real chemical reaction, to accelerate stage number 3, we need a catalysis. That catalysis, when you put in stage number 3, it can accelerate the reaction for stage number 3 by introducing a different reaction pathway for number 3. Okay, so that is the analogy between a chemical reaction and somebody traveling a journey from starting destination to the final destination. Okay, so now for example, you go back to the rate law. Okay, in the rate law, we say that the rate depends on the rate constant. The rate law. The speed. This R is basically the rate or the speed of the reaction. The whole reaction. Okay, so if the whole reaction depends on the rate determining step, which is step number 3, then the overall rate of the reaction R equals to K3. K3 is the rate constant for step number 3 and times by I2. I2 is the intermediate, which is the reactant for stage number 3. Okay, and assuming that the order of the I2 is 1, so therefore you get R equals to K3 times I2 intermediate. Okay, this is like, for example, a very simple model, but we are simplifying so that mathematically the derivation is simple. Okay, so this is a very simple model. Okay, so therefore, if stage 3 is the slowest step, therefore the speed of the overall reaction will depend only on this step, and the rate law can be given as this one here. Okay, so now we go into the steady state approximation. What is steady state approximation? This is only an approximation method. Okay, from the name, it is only a approximation method. This method is being used to actually find a derivative, what you call a representation of the intermediate, because in the rate law you cannot write R equals to a very constant times intermediate, because you cannot write intermediate. You must find a substitute for the intermediate in terms of the reactant. Okay, so that is why we use the SSA. Okay, what is the SSA? If you look at the profile of the concentration of the reactant and the intermediate and the product. Okay, in the reactant, the concentration of reactant will actually decrease, decrease until it becomes 0. Okay, but the concentration of product will increase until it become constant. But the intermediate, initially it will increase and then it become constant and then it decrease to become 0. When all the intermediate has reacted, then you have full product formation. That is what the profile tells us. Okay, now in the SSA steady state approximation, it can be only used when the intermediate concentration is constant. Okay, when the intermediate concentration is constant, then the SSA method is applicable. When the intermediate concentration is rising, the SSA is not applicable. When the intermediate concentration is what you call is falling down to zero, then that method is no longer applicable. It is only applicable to where I equal to zero. I mean, sorry, di per dt equals zero, meaning that when a di per dt is basically the change of intermediate per time, and di per dt. Yeah? So when you have di per dt equals zero, then that SSA can be used. Like for example here, okay, di per dt is a change of intermediate per unit time. When it becomes zero, it means that the rate of the formation of the intermediate is equal to the rate of destruction. This is what the SSA tells us about. Okay, so now this, from now onwards, is a very, you just consider a very simple chemical reaction, because chemical reactions are basically complex. This is only a very simple model. Okay, take for example, the reaction between chlorine and oxygen and hydrogen to give us HCl and water. Okay, this is a very simple model where chlorine reacts with oxygen to get chlorine oxygen, oxychlorine, 2ClO. Okay, this is an equilibrium reaction where chlorine plus oxygen get 2ClO. Forward reaction, the reverse reaction is back to the what do you call chlorine oxygen. So you have K1 and K minus 1. K1 is the forward reaction, K minus 1 is the reverse reaction. Okay, now the next step is the reaction between the ClO. ClO is the intermediate plus hydrogen, you get HCl and water molecule. So the second step is basically the reaction between the intermediate and the reactant, where you get the product formation. The intermediate here is ClO molecule. ClO is chlorine oxygen. Okay, so now let's say for example, if step 2 is a slower step, okay, it is a slow step, very much slower compared to step 1 and the reverse of step 1. Then if this step 2 is a slower step, the reaction rate will only depend on step number 2. Then the whole the rate law for the whole equation can be written as K2, because K2 is a constant for reaction number 2, very constant, K2 times ClO times H2, assuming that the order for ClO is 1 and hydrogen is 1. Okay, so the overall order is 2. 1 plus 1 equals 2. Okay, so this written here is the overall rate law equation for step number 2, when step number 2 is the rate determining step. Step number 2 is rate determining RDS. Okay, so now we must find a substitute for intermediate ClO. Okay, it can be done by using the steady state approximation. What does in this approximate method, it tells that the rate of production of ClO equals to the rate of destruction of ClO. That is what the SSA tells us. Okay, where this ClO is the intermediate. Okay, so here the rate of production of ClO is this rate of production. You go back, rate of production. The rate of production is reaction number 1. Number 1. Sorry, K1. K1 gives you the production of ClO. Okay. K2, K minus 1 is the destruction of ClO, because ClO goes back to chlorine oxygen. And step number 2 is also the destruction of ClO, because ClO becomes HCl and water molecule. Okay, so now here in this scheme, there is 1 production step, there is 2 destruction step for the ClO molecule. Okay, so according to SSA, the rate of production, which is this, must equal to the rate of destruction, which is equal to this. So you make this equal, now you get this expression, and you solve it, you get what you call ClO equals to this expression now. So this is what you call equation number 1, equation number 2. Okay, so you solve it, now you get this whole thing. Now you can find ClO. This ClO, this is the expression for ClO molecule. So substitute this into this equation. You finally get the rate law become this expression. So this is the rate law when the step number 3 is a slow step, and step number 3 is a rate determining step, and the rate law can be written as this. So look at the rate law. You have the chlorine, the reactant, oxygen is the reactant, hydrogen is the reactant. There is no more intermediate. So this is how the SSA method can be used to derive rate law for the to substitute the intermediate with the reactant. But again, this method is only applicable when the intermediate concentration is 0. Okay, it is only applicable when it is only applicable when the di per dt equals 0 or the intermediate concentration is basically constant. It is no longer valid if the intermediate concentration become increasing or decreasing. When the intermediate concentration is constant, then the SSA method is applicable. Okay, so that's all for it. So I end here, and I will so see you soon.